Okay, so this is the second part of 622. In the first part, we found the maximum momentum. Now we're going to find the maximum shear. So I'm going to redraw the beam, and I'm going to put this our notion of the shearless connector in. So I'll still have my pin supported A and C. When I said pin, I meant roller. So this is what it looks like. So we're going to put positive shear on both sides of this connector using Mueller-Breslau. Those are positive shears. So how would this structure move? Well, the right-hand side is going to move up or down? Up. So I'll just kind of sketch it in like that. Left side, up or down? Down. So as it goes down, it's going to seesaw over the pin at C and then turn on the link at B and then reconnect at A. So there's the shape of my influence line. So let's sketch that out. So this is the shear at E. It's a function of X. So it's going to look something like this. Now, we've talked about this before, but shear influence lines have this extra little help in that we know that as we move from one side to the other side of this fictitious shearless connector, what's the total change in the shear? 1. And we also know that these links here are the same, 4 meters and 4 meters. That means these heights have to be the same, which means that these values have to be the same, 1/2 and -1/2. And then similar triangles tells you that this value has to be 1/2. So without any really help from any other free body diagram, we've got a complete influence line for the shear at E. Do you have a question, Mr. Bird?
Yes. Do live uniform loads have to be continuous?
Oh my goodness. So, now say that again?
The live uniform loads have to be continuous?
Across the whole beam?
Can you have like 2 separate?
Yes.
Okay.
Yes. So let's see how that's going to work. So we're done with that. So now we just solved the problem. So I'm looking for the maximum shear at E, positive shear. So let's start with the problem. If I remember correctly, we had a uniform, concentrated live load of 45 kilonewtons. So there's my live load. It's 45 kilonewtons. Now, I'm trying to find the positive shear. So where should I put it? Looks like I could put it either at B or at E. They both have the same value. Whatever that is, you're going to come up with 1/2. So that's going to be a value of 22.5 kilonewtons for the shear, or contributing to the total maximum positive shear due to the live load. Then we have the live uniform load. I think this is going to address Mr. Bird's concern is where do we put it? Well, we need to put it over all the positive area. So we would start it here at 0, run it 8 meters, then stop it, and then turn it back on over this last 4 meters. Okay? So that value is 1.4. So that would be 1.4 kilonewtons per meter. Both those things are triangles, so I'll just go ahead and put the 1/2 out front. Handling the first part here, the base is 8 meters and the height is 1/2. And then this next piece has a base of 4 meters and a height of 1/2. So that's what? That's 2 plus 4 is 6, divided by 2 is 3, times that is 4.2 kilo. Is that right? 4.2 kilonewtons? Yes.
What does it represent then when you have the triangle on bottom? Why don't you subtract that from
Well,
your line?
Well, this is the live one, so I'm going to be able to start and stop it wherever I want. So I'm making sure that I get all the positive area from my influence line.
So you never, okay, see, I want to subtract that.
Not. Now you do on the next piece when we do the dead load. Now see, the dead uniform load, you don't get to move it around. Dead load usually is the weight of the beam. And the weight of the beam doesn't move around, it's everywhere. So now when I do that value, which is 0.5 kilonewtons per meter, I've got to do all these areas. So again, they're all triangles, so I'll have my 1/2. And I'll just start on the left-hand side and take care of all of them. So the first one is going to be a base of 8 and a height of 1/2. The second one is going to be a base of 4 and a height of minus 1/2. The next one will be a base of 4 and a height of positive 1/2. So these two cancel out. So I've got 4 divided by 2 is 2. That looks like 1, right? So that's just 1 kilonewton. So the total would be the sum of all those. So my maximum shear at E would be all this stuff. So what is that? 27.7? Does that look right? Did I do the addition correctly? So what would that load scenario look like? So I'd have my roller. So my dead load, again, goes over the whole structure, just like the previous problem. Dead load, and that was 0.5 kilonewtons per meter. Now the live load is a little trickier. It goes over the first 8 meters, stops, and then picks back up over the last 4 meters. That was 1.4 kilonewtons per meter. And then my actual final moving force could have been in 2 locations. It could have been here at B or E. I'm just going to put it at B.
I'm sure that physically the live load distributed.
Just like I did right here. There it is.
Like someone running across it, jumping.
Well, you got to remember we were talking before about AASHTO specifications. AASHTO allows you to represent a truck as a single concentrated force and a live load in the lane. So this could be a situation like that. Think about a vehicle moving across your structure. What if it's 2 vehicles? This part of the vehicle is on the first 8 feet, and another vehicle is on the last. There's no vehicle here. Moving on, moving off. So things move on and off the structure. That's the difference between live and dead.
Sometimes I be feeling like a dead load.
Are you a dead load?
Sometimes.
Sometimes?
When I wake up in the morning, I'm a dead load for the first 20 minutes.
That's an interesting analogy. All right. Any other questions? If not, then I'll turn this off.